Hi, my name is Gary Rubenstein, and it's April 1st, 2013. I'm doing a warm-up for a presentation I'm scheduled to do in Denver a couple of weeks from now at the NCTM conference. My presentation is called supports math teachers and gives them extra training and things like that, and they actually have paid for to go to this conference, so I appreciate that. The reason I teach astronomy to my math classes is because during the day and their shadow and the size of the shadow and the angle of the shadow, these are all things that after students learn a bit about astronomy and how it's really just geometry and geometry, they won't be able to help but think about these things, and throughout their lives they'll be seeing the moon and the sun and the stars, and this will give them an opportunity to always remember things learned in your class and to think mathematically outside of the classroom. The main resources that I used for this, mainly I used a book called History of Practice of Ancient Astronomy. I also used these two books, The Mathematics of the Heavens and the Earth, where I took the title of this presentation from, and Heavenly Mathematics. I used 3 articles from NCTM publications, one from Mathematics in the Middle School about the moon, another, this isn't the right picture, from a 1999 mathematics teacher article called Astronomical Mathematics, and one from a 2004 mathematics teacher magazine called Copernican Mathematics. I also used the Nebraska Astronomy Applet Project, which is a website that's got 3D animations that you can interact with, and it really helps you understand what's going on with the astronomy. The first day of my astronomy unit, I have my students answer a questionnaire. And it has questions that most adults don't really know the answer to, but some students maybe took earth science or something and might know some of the answers. But things like what causes the phases of the moon, or do the days really get longer in the summer, and if so, how long they get? Why is Easter always on a different day? And just questions like this. What does it mean to be a Libra? And things like this. So I give out a questionnaire to get a sense of where the students are already and get them thinking about and wondering about, what are the answers to some of these questions. At the time, you see a bunch of stars if it's clear enough. And most people probably don't spend that much time staring at the stars. But what if you were, and in this case, I'm located at about city, and I'm looking to the north, and let's see what would happen if I just watched and watched and I sped up time. So an hour later it would look like this. Stars would shift a little bit. Oh, well, here are the constellations. Now it will start moving. So 1 hour later, you'll notice that things change this way, and an hour after that changes to that, and an hour after that, and an hour after that. And we start to see that what's happening, at least when looking north, is the stars, some of them in a large circle. If I look to the south, I often see the moon. And over a period of 4 hours, where the moon is at midnight on this day, April 9th, 2013, an hour later the moon has moved. Well, it continues and it moves along with the stars, and there's 4 hours worth of how the moon has moved. And notice how the moon has stayed within this same constellation. All the stars seems to be moving along with the stars. And there's the moon at 4 o'clock in the morning. Now, if I look up at the sky around 4 o'clock in the morning the next day, at 3:56 in the morning on the next day, look what happens. The moon is no longer in the constellation Libra, but it's now moved into the constellation Scorpio. And if I go another day later, April 11th, at approximately 3:52 a.m., the moon's over here, and on April 12th at 3:48 it's a different phase. It's half moon, and one more day, April 13th at about 3:44, the moon's over here. So the moon, whereas all the stars seem to be going from east to west, the moon seems to be going slowly from west to east. On a given night, it stays within the same, if you look a day later or a couple of days later, that the moon is having its own kind of movement in the opposite direction. But it's also going around with the stars, but with respect to the stars, it's going in the opposite direction slowly, approximately 12 degrees a day. Now the sun, here's the sun just about to rise, and just before it rose, the constellation Pisces had just risen. If I look a month later at a sunrise, this is in May, now Pisces has already risen, and the sun's over here in the Aries constellation. Now throughout the day, of course, the sun seems to go from east to west, and all the stars do. But the sun also seems to be going, if you look over a period of days, a little bit from west to east each day, and that's how it kind of ends up in relations. When someone says I'm a Pisces, that means that at one time, when that person was born, the sun would be in the constellation Pisces on that day, and actually that would be not a good day to see the constellation Pisces in the sky, because the sun would be blocking it out. It's a whole different story. This is a picture of how the planet Mars has changed position with respect to the stars over about a 6-month period. It seems to be going in this direction from west to east against the stars, but then for a little while it goes with the stars, and then it goes back against it. Again, on any individual day, the planet seems to go from east to west like everything else. But over a period of days, with respect to the other stars, it makes this kind of strange movement where it goes backwards, and that's called retrograde when that's happening. The key is what's known as apparent motion. That's when an observer is moving, and the thing the observer is looking at is either still or it's moving itself. From the observer's point of view, we might see a sort of a complicated motion that other object is doing. And a nice illustration of is in the movie Airplane, in this scene that I like. Wait. So apparent motion is what an object seems to be doing if the observer really was standing still. Here's a little scene from Airplane. Try that again. Maybe not. Probably for copyright permission anyway to put it onto YouTube. Though if you go to my actual presentation, you will get to see that clip. She's spinning him around, and he's watching. You can see from his perspective how she seems to be standing still, and the room around him seems to be spinning. I have my students do an activity where they predict what it should look like person A's perspective if they're doing, in this case, person A's rotating while person B walks in a straight line, or in this case where person A is rotating and person B is going around in a circle. Here's students who are doing this activity, and they're big smiles on their face, obviously enjoying it. So then when I get into the actual astronomy and teaching my classes, the first thing I teach them is about the moon, because the moon is actually the easiest to analyze. If anyone's ever seen the moon out during the day, it's kind of puzzling because we always think of the moon kind of coming out at night, but you'll see that the moon's out in the day a lot, and there's a lot of math behind that. If you look over here at this little video, at any given time, half the people on Earth can see the sun and half can't. That's day and night. Likewise, half the people can see the moon and half the people can't. Now when the moon is over here, the people who can see the moon from, as you can see, depending on where the moon is, different people can see it. These people see the moon throughout most of the day, and there's actually 4 kind of regions. Some people see just the sun, some see both the moon and the sun, some people see just the moon, and these people see see neither object. So it all depends on where you are. So in this case, people from about 8 a.m. or 9 a.m. to 9 p.m. can see the moon, but people from 6 a.m. to 6 p.m. can see the sun, and that's why this green region is the overlap between them. A nice way to visualize the phases of the moon is to give your students a black and white cookie. In this case, I have 3 black and white cookies, one in different angles. And when you look at that same cookie from the side, in this case we see sort of a full cookie, a full moon. In this one we see half white, half black. But this is the most interesting one. When it's tilted in this way, when you look at it at an angle, you see from the side mostly white and a little bit of black, a little bit of chocolate. And that's related to why we see the phases of the moon. Here's a nice little video to show a half white, half black sphere rotating. And you can see that little crescent shape that's so sort of famous for being a shape of the moon, and gives you a little sense about why that happens. Now I made this animation where we can see the moon going around and how people on Earth would, what moon would look like from the people on Earth who can see it. So it's a full moon. Now when I make a graph of sort of the percent of moon that is white at any given time as it goes around, it looks like this. And this is a way, and this I learned this from the from that math in the middle school, from the math in the middle school exercise, that it makes what's called a cosine curve. And here's a little demonstration of why it's a cosine curve for those people who are kind of mathematically inclined. The angle between the angle here, TRM, the sun's out over here on the left. Based on that angle, TRM actually equals this angle, GMI. And the cosine of that angle is the radius of the moon times, or I should say, the length mg here is the radius of the moon times the cosine of this angle. But mg is also EF, and EF is sort of the portion of the moon we see. From C to F is sort of the white part in this case, and from F to D is the darkened part. So we end up with this equation. CF is R plus R cosine theta, which is the graph of what we saw before. In 300 BC, Aristarchus tried to measure the distance, how the distance from the moon to the earth related to the distance from the sun to the earth. In this picture, which I actually, you can see the sun here setting and the moon here in the sky. Well, Aristarchus measured that angle and approximated it to be about 87 degrees. He said this is the configuration of the earth, the sun, and the moon when we have this half moon. And he estimated this angle, ABC, to be about 87 degrees. Well, if it is 87 degrees, we can use trigonometry to show that CB, distance from Earth to the moon, is about 1/19 the distance from the Earth to the sun. Now this was off because it's truly 400 times, the sun's truly 400 times further away. The sun's also 400 times bigger than the moon, which is why when we have a total eclipse, the moon seems to cover that sun. Now Aristarchus was off by a big factor. That angle actually is not 87 degrees, it's more like 89.5 degrees. But he only had Aristarchus said it was between 18 and 20 times as far because he didn't have cosine, he didn't have trigonometry. He just had what we'll call pre-trigonometry. Basically, they had this idea that in this configuration, the ratio of the two angles was always bigger than the ratio of those two sides. We can see this still here is better for it. The ratio of the two angles was always bigger than the two hypotenuses, BC over BD. But it was also less than the ratio of the two bases, AC over AD. And that was an inequality that allowed them to do this approximation, but it was pretty complicated, and I don't know why this image is here, because that's not what should be there. Some cool proof. Oh, here it comes. This is a really fast write-up of Aristarchus's proof, along with the diagram on the left. of how he proves that the ratio was between 19, 18, and 20 times as far. It was pretty cool. I have to fix that. Now, in ancient times, they created a model that was useful in trying to predict where the sun, where the moon, where the stars, where the planets would be. And this is called the celestial sphere model. And in it, the Earth is in the center of the Earth. The Earth is in the center of the universe. And the stars and the sun and the moon are all kind of on this giant sphere that's rotating around us approximately once every 24 hours. And this model, even though it's not technically true by today's standards, is very useful still, and we still use this model in navigation and in describing the position of stars as if they are on this giant celestial sphere, and they have kind of a latitude and a longitude on it. So if we take a look here, here's everything rotating from east to west. There's Mars and there's a moon there. Someone who's at 40 degrees latitude sees the thing this way, and this is why we see our stars rising in the east and setting in the west. But if we stop the motion of the celestial sphere, we can see that the sun, the planet, in that case Mars, and the moon are moving in the opposite direction steadily. Moon is moving pretty quickly. The sun's moving slower. Mars, though, check out what it does here. It's going from west to east, then it starts going from east to west momentarily, and then back from west to east, retrograde. They needed a model that would be able to describe this and predict it. Latitude and longitude on the celestial sphere, the words for those are declination for latitude and right ascension for longitude. And when you learn this astronomy, it gets confusing with all the expressions. There's a point on the equator, the celestial equator, called the vernal equinox. I'll tell you a little bit about that after. But right ascension is measured in degrees from that, and declination is degrees going from the equator towards the North Pole. Declination is measured in degrees from 0 to 90, or negative 90 to 90, and right ascension could be measured in degrees from 0 to 360, but actually they measure it in hours, from 0 hours to 24 hours, where an hour is 15 degrees. There's also something called the ecliptic. Now, the ecliptic is another, what's called a great circle. It's a circle the same size as the celestial equator, but it's tilted degrees, and the sun and the planets and the moon generally stay either on or very close to this other circle. And when we measure, if we use that as our reference point, then we have what's called celestial latitude and celestial longitude, which is the location of the star from going in this other direction. And that is useful for talking about the planets and the moon and the sun, which seem to stay on this. So this star up here has one set of coordinates using declination and right ascension, but if I'm using celestial latitude and longitude, it would have a different set of coordinates. And converting from one set of the coordinates to another is complicated. There is a third way of looking at coordinates, and this is from the perspective of the person and where they're standing. So if I go over here, it's called a horizon diagram. If I take my location there, about 40 degrees, and I flatten myself out to a disk, then I rotate the disk, I have what's called a horizon diagram. And the horizon diagram is, unlike the other two that are, the coordinates are not, they're sort of from a perspective of outside the sphere. This one is from inside the sphere. So someone in a different horizon, when they measure the coordinates of the star using something called azimuth and altitude. Altitude is kind of the latitude from that observer's point of view, and the azimuth is kind of like the longitude. These things are all measured in degrees because they are basically angles. So those are three coordinate systems that you have to get familiar with as you read about this stuff. Now, one cool thing we can do, our first sort of thing, is that we can determine our latitude at night by looking up at the sky. You see, the North Star is located directly above, at the very tip of the celestial sphere. So people standing on top of the Earth at the North Pole would see the North Star directly above them. But somebody over here at 70 degrees latitude, see, latitude is measured in degrees because the latitude is this angle, this ABC angle, that's their latitude. When they look straight up, they see D. They see this point. They don't see this. They have to look to the left a little bit, or look north a little bit, sorry, to see this North Star. Well, the amount they have to look is about 23 degrees in this point. And over here at 40 degrees, where we are in New York City, when you look up, you see this, you have to turn your head 40 degrees to the north to see the North Star. About 50 degrees. Well, the amount you have to tilt your head, if you do 90 minus that, you will get your latitude. And the reason this is angle CEB is practically 0 degrees because it's so far away. Angle GCE is an exterior angle, so it's the sum of this exterior angle is the sum of this little angle CBE and 0. And that means that this angle DCE is pretty much the same as angle ABC, which is your latitude. So you can figure out your latitude, and people at different latitudes see different night skies where everything's rotating around the North Star, and the North Star is either directly directly above you if you're at the North Pole, or it could be, you might have to angle to see it. Longitude, well, even though this latitude was figured out in BC times, they didn't figure out longitude until maybe the 1600s or the 1700s. It required making a very accurate clock, and there's a nice book about that called Longitude. Another thing you can do, once you know the places that are on the same longitude line, you can figure out how big the Earth is. So Chicago's at 40 degrees latitude, New Orleans is at 30 degrees latitude. We know that Chicago is 830 miles from New Orleans. The angle between Chicago, the angle there, CON, is 12 degrees. It's the difference between the two latitudes. A simple proportion, 12 to 360 is 830 to x, tells us that the circumference of the Earth is approximately 25,000 miles, which is accurate. Now, the sun we saw before is on the celestial sphere, but it's moving a little bit, and I just want to show you a little bit about how we can try to calculate first understand why days get longer in the summer and shorter in the winter, and how to calculate how long a day might get in the summer at a particular latitude. So take a look over here at this animation. Here's the sun going around the celestial sphere from east to west. That's happening around spring. Moves a little bit on what's called the ecliptic, this other circle, 23.5 degrees tilted, and then the sun goes around the Earth celestial sphere this way. And in summertime, this is the model, the sun goes around the celestial sphere, it ends up all the way up here on the ecliptic and goes around this. And as the year goes on, the sun slowly moves, it gets to autumn, and then to winter over here. At winter, the sun is on the celestial sphere this way, so when it rotates around, the sphere rotates, it goes like that for that day from east to west, and then back. So the sun changes its latitude throughout the year, or I should say its declination. Now, what's really going on, just because a lot of students already know that, yes, no, the sun's not going around the Earth, but here's why it's it's an okay explanation. Oops. This works 23.5 degrees. So in summer, the Earth looks like this. The sun seems to be doing this when the Earth rotates in the summer. seems to be going around a circle like this because the Earth's tilt. When the Earth revolves around to wintertime, it keeps that tilt, so now it's winter because the sun's going like this as we rotate around, or sort of underneath us like that. And when we get over here to spring, there's actually a nice 90-degree angle here. As you can see, if I rotate my Earth so it's pointing straight up, What went wrong there? Oh well. Well, this means that in Raiders of the Lost Ark, Indiana Jones would not be able to just go to the map room at a particular time, on a particular day. I'm having some problems with my animations. Oh well. In ancient times, and even nowadays, they had this device called the armillary sphere, which looks like this, and it lets you kind of move the sun around and see the Earth there in the middle. We still see this tool in sculptures in New York City. There's two celestial sphere models. The Earth is way too large in this picture, the ecliptic circle, which is kind of neat. And everyone needs an armillary sphere, apparently. Even the Wicked Witch of the West. Now, or perceives, because over here we have the sun going around it. Oops. Over here we have 12 hours of daylight, 12 hours of nighttime. But in the summer, the sun's up here, and we see that more sun, more day. And one of the things I taught my class, which they really liked, was how to calculate how many hours of daylight there are, specifically at the longest day of the year. It comes down to this geometry question. The sun's circle is over here, and our horizon, where we are, is this circle over here. The sun's we're going to have daytime for all this spot and nighttime down here. So the question really is, what's this angle? If I figure out how much nighttime there is, and then subtract from 24 hours to get the amount of day there is. So let's see how we do that. Well, if we draw in a bunch of auxiliary lines, it's going to enable us to say, here's a top view. We have, this is the sun circle. A is the radius of the sun circle. X we don't know, and A minus X we don't know, but our goal is to get this angle EOF. Here's a side view. We have this sun circle is this line COD, but we have on this picture two angles. One is angle ARC, which is 23.5 degrees. That's the declination of the sun at what's called the summer solstice. That angle could be something different also, but we know for sure what it is at its sort of highest latitude. Angle ORG actually our own latitude. That's a little tricky to see why, but I'm going to leave that as a detail for now. I'll just tell you that it is. So here's our picture, and our goal is to find angle EOF. Now angle FOE, because of this right triangle here, if I could get A minus X over A, cosine of this angle would be A minus X over A. So my goal is to, if I could get A minus X over A somehow, I could do the inverse cosine, double it, and subtract that. Multiply by 24 hours. FOE over 360 would be the percent. 20 times 24 hours is the amount of nighttime. Daylight would be 24 minus that. But this is very hard because even though I know what angle GRO is, and I know what angle ARC is, and it's 23.5 degrees, I don't know what X and A minus X are. However, check this out. From the side view, tan of angle C, which is up here, which is the same as angle ARC, is B over A. Now we don't know B or A. And tan of GRO, which is tan 40, is A minus X over B. Now we don't know any of these things. However, check this out. If I multiply these two things together, the B's cancel out, and I learn that A minus X over A is tan 23.5 times tan 40. That's tan of 23.5 is the sun's biggest declination. Tan 40 is my current altitude, my latitude, that is. So I figured out a minus x over a without getting either of them, a or x. And once I have that, I can plug it in over here to get the angle, turn that angle into percent, and subtract from 360 to get about 15 hours of daylight in New York City. Now you can do this with different latitudes, and you could even do it with different declinations of the sun, but the 23.5 will always give us, that's the highest declination we ever get of the sun. Now, in ancient times, they noticed that the seasons were not all the same length, and that's still true. And they wanted to explain this somehow. So the sun goes around this ecliptic circle, but it seems to go faster sometimes than others. But it was very important for them back then that uniform circular motion was a big part of what they thought was true. But here's what they noticed. They noticed that the sun seemed to speed up throughout the year as it got through, and now winter and fall are shorter than summer and spring. And they didn't know why. Like right now, it's about 92 days for spring, 93 days for summer, 89 days for fall and winter. And they wanted to know why this is. So they came up with a theory. And the theory was that maybe the Earth is not in the center of the circle that the sun is going around. So here I have going around that one at a constant speed. But it seems to be going faster when it gets closer to the Earth. Just like a train seems to be going faster when it's going right by us than it does when it's far away from us and we see it slowly moving, or like an airplane. So they came up with a theory that because Earth being in the center of the universe was one of the primary things that Aristotle said. But they had to come up with this compromise. And this was back in BC times. They had to come up with this compromise. And it was better than the other compromise, which would have been that the sun was changing speeds. Turns out that the Earth is changing speeds, and it's in this diagram. I have the number of days are turned into arc lengths by degrees. So Kn is spring there. It's 91.46 degrees, 92.28 degrees. I have all these angles here, and the goal is to figure out how big CO is compared to the radius of the whole circle, and that's what's called the solar eccentricity. And it turns out it can be done pretty quickly and easily. We know that these two arcs, the summer and the spring arc, add up to 183.74 degrees, but we also know that SKQ is 180 degrees. Half the circle sees the center of the sun's circle. Well, QL and SN are equal to each other, and from that we're able to calculate how big they are. Once we know the length of QL, we could draw in this perpendicular VL. The arc QL is the same as the angle QCL, so we could use sine to figure out the length of VL, which is also the length of CU. Now they actually get to invent trigonometry, the sine tables, to do this calculation. Now they also know that PK, 92.28, minus 90, which is PQ, minus the 1.87 I just figured out, is a 41 degree arc. That means that CT is the same as PK, but PK is related to angle WCK, and it's a right triangle, so we could use sine again to get the length of. Learn is that using Pythagorean theorem on this little triangle here, we could calculate the length of CO, which is 0.0334. This is not drawn to scale, but the result is that the sun is about 3% off of the center. Now this looks like one of those questions we teach in trigonometry where we have all kinds of arcs and angles all over the place, and it's not very inspiring. But this is an eccentricity using trigonometry, like that. Now converting coordinates is something I learned from the book Heavenly Mathematics. The idea is Ptolemy, in his famous astronomy book, uses ecliptic longitude. So he would give the position of this sun based on its longitude and all the planets on this ecliptic. But to convert this into right ascension and declination is a bit tricky. A lot of different cultures worked on this. I could draw in some auxiliary lines, and we get this cool picture over here. It's got a lot of right triangles in it. So in the book Heavenly Mathematics, they show you how to convert longitude. If you know the longitude and the ecliptic, which we do, the longitude of the sun at that time, I have this formula wrong. I think it's longitude equals declination times, no, I see. Declination, and we can calculate it by multiplying the sine of the sun's current longitude. The sun moves around on the ecliptic from 0 to 360 in a year, multiplied by the sine of the ecliptic. This type of calculation was so common in the old days, where you're multiplying two sine values together, that the original logarithm tables were of sines, so that you'd be able to do this more easily. Now, when we hear the term retrograde, it means that the planets seem to move around from east to west. The planets seem to go from west to east, generally, but at a certain period of time, some planets seem to move backwards across the celestial sphere, which they needed to figure out. So the reason this is really happening is that the Earth and Mars are both moving around the sun in an ellipse. But from Earth's perspective, Mars seems to be doing something like this. It's far away, it's far away. It seems to be moving backwards and then goes forward again. That's what was really happening. But they didn't know that back then. So Ptolemy had a great explanation, which is on its own circle going around the Earth, and Mars itself is moving around that circle. Notice how this makes similar loops. And I made with the size of what's called the epicycle, and also the speed that epicycle, that it's moving around the epicycle to produce different types of, and also he also has the center of the Earth moved off of the center, so that Mars is not going around the Earth. Mars is going around a different circle, but it's not going around in constant speed around that circle. Even it's going in constant speed around another point that's called the equine point. So there's a lot of compromises Ptolemy had to make. That the Earth, that everything's moving around in perfect circles, which is great. It does solve some mysteries, so Copernicus had to compromise also. One compromise he did is he moved the center of rotation for the planets not at the center of the Earth, but near the center of the Earth. Small epicycle for the planet to go around. So now the planet was not actually going around. It looks like a circle, but it's somewhat elliptical. And so messing around with these parameters, you can get something that agrees with what is really happening. The 1999 article and the 2004 article, I learned something I found very interesting, and my students liked it also. And it's how can we figure out how far away the planets are, and also how fast they're going around the sun. And this was a good article. I really liked it. I'll explain how this works. Here's the planets. Here's Earth, Mars, and Jupiter going around, and Mars. When Earth and Mars get in this configuration, it's called opposition. You know this happens is that if you look up at midnight, you'll see Mars right up in the sky in the highest point. So what they've done along it is between two oppositions. In this case, it was 779 days from when this thing started to when it hit this point. So Earth sort of lap Mars. a second. I got to do that again. Sorry. So here's everything going. Okay, here's Mars and Earth at opposition, and 777 days later, they are at opposition at 2.13 Earth years. But Earth has lapped Mars, so it's really 1.13 Mars years. So 2.13 Earth years is the same thing as 1.13 Mars years. That a Mars year is going to be about 1.88 Earth years, or 6.85 days, and it's true. Now, to get the distance from the Mars to the Sun, we wait until, in this case, 107 days. This is called quadrature. That's when the Sun, the Earth, and Mars make a 90-degree angle. And you know this happens. You can tell this is happening when the Earth is, these people are at noon. Earth is going this way. These people are at 6 a.m. These people are at 6 p.m. So people at being Mars right above them, or people at midnight are seeing Mars just start to set. Well, this creates a 90-degree angle. We can make a right triangle here, and we can say that this angle from here to here, 106 days, 107 days, is about 105. That's how many degrees this angle is. But Mars, because we calculated Mars's year to be 689 days, in that 107 days, it's only gone 16%, which is 56 degrees. If you subtract those two angles, we get. Now, from the Sun to the Earth, we call that one astronomical unit. That's about 93 million miles. They didn't know that until like around 1680. So up until that time, you could just do things in terms of the astronomical unit. Well, using trigonometry, we can do the cosine 49 as astronomical unit over x, which makes it the Sun as the Earth is. And that's true. So those are two calculations that I learned from Mathematics Teacher Magazine, 1999 and 2004. We could pull in and look at what happens is that the Earth is going much faster than Jupiter. So when the Earth makes its, it gets quadrature after only 89 days. And it gets opposition again after only 398 days. So 1.09 Earth years is 0.09 Jupiter years. From that, you can calculate Jupiter's to be about 12 years, how long it takes to its orbit. As far as its distance from the Sun, we end up with a similar calculation, and we learned that Jupiter's about between 5 and 6 times, and that those are both correct. So those are very neat things that I learned.